Good morning. I'm sorry for the technical problems. It's a pleasure to be back to live workshops. Okay. I'm not sure how it's working at your home institutions, but for us, since we have to continue stream our classes, the students actually prefer to stay at home. So I'm teaching a course that has 120 students registered, and there's maybe 10 students in class or something. So it's actually any physical presence I can get, I actually really appreciate. So this talk is about lossy compression, actually of general data structures in the program I wrote on general data structures. This is joint work with Erwin Riegler, who is in a senior researcher in my group, and Günther Kolliander from the Austrian Academy of Sciences. In a nutshell, what this talk is about is, so nowadays there's, of course, it's all about high-dimensional data, but often data in high-dimensional ambient spaces has a low-dimensional structure. And these structures can be manifolds, they can be algebraic varieties, they can be fractals. There's all sorts of structures you can envision. And if you want to compress low dimensional data in high dimensional ambient spaces, you would think that what your compression algorithm, and I will talk about what I mean by lossy compression, would somehow operationally take into account the low dimensionality of the data. So the question is, if you have a low dimensional manifold in a high dimensional ambient space, so your data lives on the manifold, can you come up with ways of compressing the data that would be commensurate with the dimension of the manifold? And this is just one of many examples. And what we want to do here is we want to build a general theory that would somehow adjust the compression limits to the dimensionality of the data in the most general context you can think of. And let me, so now something is not working. Sorry, I have to, cannot swap slides. Ah, okay.
Maybe now.
Now it works. Okay, thank you. Sorry. Okay, so for example, manifolds, I mean, as they occur in compressed sensing, machine learning, image processing, handwritten digit recognition is probably the most famous example. There is this work by Simar et al., Trevor Hasty. They look at 8x8 images of handwritten digits, and the set of vectors corresponding to one digit is found to be essentially 7-dimensional in this case. So this would be an example of 7-dimensional data in a 64-dimensional ambient space. And the idea or the question that we're asking is, can you compress this data in a lossy fashion? So you would have a certain compression rate and you would get a certain distortion with it. And again, I'll introduce it in a second. So as to take into account the 7-dimensionality of the data. Or if you have fractals, as they're used in image compression or modeling of Ethernet traffic, and there's many other applications. Of course, that's also something that has a low-dimensional effective structure. We will be dealing a lot with the counter middle third set and looking at compression of that kind of set. Good. So what is the language that we're going to use? So this is the language of rate distortion theory and quantization. So I would like to briefly introduce these theories. And if you have any questions about their operational significance or the quantities used, please let me know. So this is the probabilistic setup. And we assume that we have a space X that supports our data. So these are Borel spaces. And we have a space Y into which we compress our data. So you can think of a real number that you want to quantize. So let's say you have a real number on the interval 0, 1, and then you want to quantize it to a certain set of values, let's say n of them, and you choose them, the quantization points equally spaced. So that would be a mapping of the data from the space X into a space Y. And we use different spaces because you will see later that gives us added flexibility. And there is a case actually to be made for this flexibility. We look at compression of IAD sequences, so independent, identically distributed sequences of random variables that take values in X. And we look at source codes, so-called source codes of length L. These are mappings that map XL into YL, and there is a distortion function that we call a single letter distortion function rho, but we actually make it into a multi-letter distortion function by taking the average. Now, the quantities that we're going to be interested in are rate and distortion. What do we mean by rate? Well, by rate, we mean that for every letter, and when I say letter, I mean one random variable, we have available, and you can replace this E by 2 to the R possible values that the mapping or the that we map to. Yeah. So for example, if you have a real number in 0, 1, and you have 8 values to represent it, then that would be 2 to the 3 bits. Now, why E instead of 2? Well, if it's 2, it's bits. If it's E, it's nuts. So this is something in information theory. Mostly people use bits in the base of 2, but in this talk, we wanted to avoid having all the log to the base 2 of E's over the entire paper. So that's why we use E. But you can think of this as 2 to the R. And R is the number of bits. So, and then of course, it's E to the LR because we have L letters. So you will ask yourself, well, wait a moment, if we compress IAD sequences, why do we look at mappings that actually map sequences of length L onto sequences of length L? And it's actually one of the most striking features of rate distortion theory, that joint encoding works better than individual encoding, even for IAD sequences. And so this is, the first lecture on rate distortion theory in information theory. This is kind of the first statement you should make about rate distortion theory, and it has to do with geometry. So essentially, if you do independent encoding, then you get rectangular tilings of your space, and those tilings don't optimally cover your space or fill your space. So that's the underlying reason. So this joint encoding aspect is a very important one. So in the first part of the talk, we'll be dealing with rate distortion theory, which goes as follows. You have R bits per letter. So you have a total of LR bits for a sequence of length L, and you have a certain distortion that is allowed. You take the expectation over your multi-letter distortion function, and you're asking yourselves, well, if I want a certain distortion, how many bits do I need to have at least in order to be able to encode my sequence of IAD random variables with that distortion? Or you can turn things around and you can say, if I have a budget of R bits per letter or a total budget of LR bits, or nuts for that matter, what is the distortion that I should expect? And the question is, how can we characterize the so-called achievable pairs R and D? And the answer is given by, as I said, rate distortion theory. So the rate distortion function is this quantity here. Now there's a number of comments that I want to make on this. So it's the inf over mutual information between X and Y. The way to think about mutual information is it's a Kullback-Leibler divergence between the joint and the product of the individual distributions. So if your random variables X and Y are independent, it's 0. If they are fully dependent, it's maximum. It's actually the entropy of X. So the rate distortion function, the way you can think about it is the following. So this mu y conditional on X, you can think as a conditional density that takes X into Y, if you like. So over all the conditional densities that give you a distortion of D, what is the minimum rate of transfer you need from X to Y? Okay, so you fix a distortion and you're asking, if I want to map X to Y with that distortion, how much rate in terms of number of bits do I need to transfer from X to Y? Okay, so that's mutual information. Now, one of the most famous results in rate distortions here, going back actually to Shannon, is that all the rates greater than Rx of D, where Rx of D is the so-called rate distortion function defined here, are achievable, and rates below are not achievable. What do I mean by achievable? What I mean by achievable is that a pair RD is achievable if it is L achievable for some L. So if there is an L so as to have this inequality satisfied, and this here satisfied. So you have a certain budget in terms of number of bits, and you have a certain distortion that you're guaranteed. So that's rate distortion theory. It tells you what the limits are on compressibility. So you fix the distortion, how much information do you need to transfer from X to Y, so as to be guaranteed that you can achieve that distortion. Is that more or less clear? Because that's going to be instrumental for the first part of the talk. And there's this aspect of joint encoding. Any questions? Yes, Felix. So you assume, like, did I get this correct, that you assume that this variable X is already discrete? No, actually, that just is a Borel space, and you can do whatever you like. Because this GL of X. Okay, so the idea is that you can quantize. Yeah. Yeah. So you can think that's why I kept talking about quantization, because indeed the value set that you map to is going to be of that cardinality, and that is discrete. But originally you can start. Yeah. Right. Yeah. Just put a PDF on the interval 0, 1, whatever. So yeah. Okay. Good. Any other questions? Good. Okay, so then let's continue. So the rate distortion function is the main currency here. So the minimum amount of information we need to transfer from X to Y in order to get a certain distortion. Think of the example that I gave you, a real number in 0, 1. If you have 3 bits, so then you have 8 quantization levels, then it's clear that your error is going to be essentially 1/8, right? Or I mean, depends on how you measure it, of course, it could be square error or whatever. Now, having said that, analytical results for the rate distortion function are notoriously hard to obtain. In fact, most of the cases, it's really, I mean, there's very few results actually on this, because it's this intermization here, and mutual information is a difficult quantity, and so on and so forth. So what are the known results? There are so-called Shannon lower bounds on the rate distortion function for discrete and continuous random variables. Those are bounds that are not explicit, so they typically involve, as you will see in a second also for us, some kind of further information over some parameter and so on. There is a case where X is Y is RD equipped with a semi-norm. In this case, the Shannon lower bound for purely continuous random variables, so the discrete component is 0 and the singular component also. In that case, you can get an explicit expression, and there is a Shannon lower bound for so-called rectifiable random variables. So just a few comments about rectifiable random variables, because it's something that you're not going to use it a lot in this talk, but still I think it's good to see. So a rectifiable set is actually a set obtained by mapping, and this is not, I mean, yeah, these are subsets that are bounded, Lebesgue measurable. You're mapping from Rm into Rn, and these are Lipschitz functions. So you can think of this as countable unions of manifolds, if you like. So that's a rectifiable set. And then you take the Hausdorff measure and you restrict it to a rectifiable set. So you put a nice random variable on your rectifiable set. So that's a rectifiable random variable. Now that accounts, or rectifiable sets and rectifiable random variables account for a number of interesting structures. As I said, countable unions of C1 submanifolds as used in compressed sensing and spectrum blind sampling, smooth submanifolds, block sparsity, low rank matrices, or even fractals. So whenever you have an attractor set that satisfies the open set condition, like the middle third Cantor set, Sierpinski gaskets modified from Koch curves, and so on. So there is a theory of compressed sensing that we called lossless analog compression, developed in 2018 for rectifiable random variables or vectors. In that case, it turns out that modified Minkowski dimension plays the role of the sparsity level, and you can actually show that even if you don't know the support set, and the support set can be a rectifiable set, you can compress all the way down to the Gini limit, which is the limit that you would get if you knew the support set in the deterministic theory. Okay. But that's not the what we want to do in this talk here. What we want to do in this talk here is we want to build the general rate distortion theory, and I would like to go back here briefly. The first thing that we do is we actually try to get a lower bound on the rate distortion function that would contain those known results as special cases, including for rectifiable random variables. So now we start developing the theory proper. And the currency that we're going to be interested in is what we call the rate distortion dimension of order k. And I will be specific in a second about this. Let's look at the rate distortion function for compressing a Gaussian random variable. In this case, the rate distortion function is essentially log 1 over distortion. The quantity we are interested in, the rate distortion dimension, is the factor in front of the log. And if you like, this counts the number of degrees of freedom. And it will turn out that it's not going to be, so the dimension, rate distortion dimension, we call it of order 2. Order 2 is we raise d to the power of 2, and I'll go back and explain where all this comes from. But essentially, if you have 1/2 here, the rate distortion dimension of order 2 would be equal to 1. So from now on, whenever I say rate distortion dimension, just think of number of degrees of freedom. Okay, so if you have random vectors or variables that live on manifolds, then somehow you would like this rate distortion dimension to be equal to the dimension of the manifold. Or if it lives on a fractal, you would like this factor in front of the log to be equal to the fractal dimension. Or if it lives on a hypersphere, then this should be the dimension of the hypersphere. So that's the question. Can we build a theory that would always extract this dimension and would allow us to compress all the way down to that dimension limit, even though the ambient space may be high dimensional? So that's the rate distortion dimension. And this power k here comes from the fact that we have a metric space, this metric omega, and then, for example, some norm, and then we would look at our rho x of y as omega to the power of 2. So I wouldn't bother too much with that. It's just, so this rate distortion dimension is the pre-log essentially, and the Gaussian is the reference case. So it counts degrees of freedom, okay? That's what we're interested in. Now it turns out that there's an interesting special case. If you have a self-similar distribution and some additional mild technical assumptions, then the rate distortion dimension can actually be explicitly expressed. And it's given by the Hausdorff dimension of your measure. And this is the Hausdorff dimension of the smallest Borel set that contains essentially or supports the random variable, if you like. So those are the kinds of quantities we are interested in, the lower and the upper rate distortion dimension. And the distinction between lower and upper is just for technical purposes. So if you like, in the first part of the talk, we will be asking, we're talking about lower bounds on rate distortion theory. We'll be asking about the prelog that comes with those lower bounds. And the question is, can this prelog reflect the dimension of the object that we are interested in? And as I said, manifolds, fractals, hyperspheres, whatever you have it, and even more general than that. So we need to build a language for that contains all this. But the first step is actually to come up with a rate distortion lower bound that would contain all the known results as a special case. And this turns out to be possible by building on a technique developed in a beautiful paper by Cesar in 1974, where we get a lower bound. We call it Shannon lower bound because it's of that style, but it's general in the sense of applying to very general random variables and arbitrary x and y spaces and distortion functions that is equal to the generalized entropy. So this is just the entropy of a random variable if it's discrete. And p of x are the probabilities. It's minus the sum over all x, p of x log p of x. So if it's a uniform distribution, you have maximum entropy. If all the probability mass is allocated to one value, you have minimum entropy. There's no uncertainty in revealing the outcome of the random experiment. So that's entropy minus, and then you have this here. So this is what I mean by all these results that are not explicit. They involve some kind of infimization here. So we need to compute this quantity here, this nu of s here. And we are going to actually compute an upper bound on this nu of s here. And that upper bound inserted in this lower bound gives a further lower bound. So that's what we are going to do in the first talk. So let me tell you how we do this for general spaces x and y. So we, well, first of all, let me tell you that this lower bound that we get contains all the known lower bounds. For discrete x, it recovers the Shannon lower bound, with this generalized entropy here being given by the classical Shannon entropy. For continuous x, it boils down to the Shannon lower bound for continuous random variables, with this generalized entropy being equal to differential entropy. Likewise, we recover the result by Colliandro et al. For rectifiable random variables. And then there is this one explicit result by Yamada, which we can also recover. And there is a quantity here that we are going to use later, but never mind the details now. I'll come back to that. So now, what is the language that we're going to use? So the language that we're going to use, I mean, this should be somehow minimal in terms of the structural requirements that we have. So what we're going to look at is small ball probabilities, if you like. So we actually are going to work with probability measures that are rho subregular, and rho subregularity means that the probability mass contained in rho balls around y of radius delta is less or equal than a constant times delta to the power of m. And this m actually will be an important quantity. It's our subregularity dimension, and c and delta 0 we call the subregularity constants. And I'm going to show you how you can work out this subregularity for hyperspheres, for manifolds, for fractals, and so on. So they all satisfy this subregularity condition. And sometimes I will say subregularity with equality. In this case, I will say there's a lower bound and there's an upper bound, and they actually meet. Okay, so good. So that's the language: rate distortion theory and subregularity, and we're going to be after this dimension here. So now, how is that general, and how is that going to help us to build this general theory? So first of all, subregularity examples. Lebesgue measure is subregular indeed with equality of dimension m is equal to d, and we work in Rd here. Measures on discrete sets of subregularity, and the dimension is 0. And whenever you put the d-dimensional Hausdorff measure restricted to a set X, that is, for example, a compact convex set that spans, or a d-dimensional compact C1 submanifold, or a self-similar set, then your subregularity dimension will be equal to here the dimension of the set, because it's spanning, or the dimension of the manifold, or the fractal dimension here. So these are all examples that satisfy the subregularity condition. So this is not something that is esoteric, and I'm going to show you how to work this out for hyperspheres in a second. Now, this is the lower bound that we get. The only thing I would like you to focus on is actually the only quantity that depends on the distortion d here, because for now we are going to be interested only in the prelog. So you take this down, you get m divided by k. And if you have the case order rate distortion dimension, then you raise d to the power of k. So you get an m in front of the log here. So that is actually your subregularity dimension, your dimension of your manifold, of your fractal, and so on. So that's what we're going to be after. But it's just a lower bound, right? So we still have to talk about upper bounds. And in fact, we will want to match the upper bounds with the lower bounds later on. Okay, how do we use subregularity? Well, we started by looking at Yamada's derivation of who has the only explicit result, and he evaluates the equivalent of this quantity nu of s that we find by using the fact that, I mean, he has an absolutely continuous distribution and shift invariant measures, and then you can actually, you know, do the simple transformation, and you work with polar coordinates, and you can integrate things out. So here is actually the first technical argument that we use, and it's strikingly simple. So all we use is actually a so-called layer cake argument, or Fubini's theorem, applied to the quantity that we want to integrate over. So we start by writing the integral f of x d mu of x in this form here. So this is then f of x, of course. And then we use Fubini's theorem, and we rewrite this here as the integral over the measure of all x's that satisfy t less or equal than f of x. And since f of x takes values in 0, 1, then we can restrict integration to 0, 1. And then we perform a variable substitution, and we set t is equal to e to the minus u, and or u, sorry, u is equal to e to the minus t. And then you get this here. And here, lo and behold, you get actually something that we know how to work with, given that the measure is subregular. We get a probability mass that resides on the row ball centered at y of radius u divided by s. So here we insert a subregularity condition, and this gives us the gamma function, and that is actually then what we get here in our lower bound. That's all. So these are the two things. So layer cake argument, Fubini combined with subregularity, and that's it. Okay, it's nothing more than that. And now what you find is that under the assumptions of the theorem, you always have the lower rate distortion dimension to be greater or equal than m, your manifold dimension, your fractal dimension, your hypersphere dimension, and so on. So this generalizes results by Kawabata and Dembo to arbitrary x, y, and rho x of y. So that's important. So it's, you see, it's very minimal, and it doesn't need anything beyond subregularity. And this is why it works for general structures. So now the subregularity constants delta 0, c, and m, the dimension, they depend on the geometry of the structure supporting the data. And then there is this term h mu of x here that we want to be finite, this generalized entropy. So that depends on the shape of the probability density function. So this just, I mean, we often will require that this be finite for things to work out, but that's just some regularity condition. So the important thing is this exponent here. Okay, let's see now, by way of a simple example, how easy it is to verify subregularity. So you put the Hausdorff measure on the sphere S of R, and then you compute mu of b rho y and radius delta. So you put y here, and what you do is then you want to compute the probability mass that resides here on this intersection. So all you do is you recognize that this probability mass, since we are uniform on S of R, is the arcsine of delta divided by R. It's actually 2 times arcsine divided by 2 times pi of R. And then you upper bound this for all delta that are less than delta 0 and less or equal than R, because if delta 0 becomes greater than R, then of course you can exceed the radius here, and then you have captured all the probability mass by this here. And this is your subregularity constant, and your exponent is equal to 1. And this is also the dimension of the sphere that you're interested in. And then you go to higher dimensions, and you use the spherical cap formula or hyperspherical cap formula to get exactly the same thing. So you have subregularity of exactly the dimension of the object that you're interested in, okay? So that's the name of the game. Throughout the talk, we'll be playing this game here. So further examples, and then you can insert in the lower bound. And indeed, if you evaluate the lower bound, you get the exponent here to be d minus 1 divided by 2. And then you raise d to the power of 2 because it's the RD dimension of order 2, and you get your desired lower bound. The rate distortion dimension is greater or equal than d minus 1, okay, the dimension of the object you're interested in. Now, another example, Grassmannian manifolds. So you consider the Grassmannians consisting of all R-dimensional subspaces of RD. The distance measure we use is chordal distance. So these are the principal angles and the standard notions in this business. And then you put a uniform probability measure on G of R and D. And you can verify subregularity. And it turns out, so this was done in a different context. It turns out that the subregularity dimension is exactly the dimension of the Grassmannian. You take your rho function to be equal to the chordal distance squared of x minus y, and then you evaluate your lower bound, and then again you get that the lower rate distortion dimension is greater or equal than mg, which is the dimension of the Grassmannian. There is something interesting here, namely to show you the added flexibility that you get if you allow x and y to be different. A simple example, if x is g r of d and y is g s of d with s greater than r, then you can think of your quantization process as mapping r-dimensional subspaces into s-dimensional subspaces, where s is larger. So you have more space, essentially. And it turns out that this dimension here will be smaller. So if you make more room in Y, you actually get a lower dimension, you get lower complexity in quantizing. So you have more freedom, and this is reflected by a lower dimension here, okay? But all these things only become meaningful if we can match those lower bounds by upper bounds, which we're going to do in the second part of the talk. And the last example I would like to show you is fractals. So we consider the middle third Cantor set. So just to give you an idea of what we're doing, you have the interval 0, 1, and then you either go left or you go right. If you go left, you have the mapping x divided by 3. If you go right, you have 2/3 plus 1/3 of x times x, and you keep going. So that's what we're looking at. And then we put m-dimensional Hausdorff measure with the right m, which is log 2 divided by log 3 for the middle third Cantor set onto this set. And you can actually very easily verify subregularity in this case. The way you do this is you look at, for example, layer 3 here. You choose a delta that satisfies this double inequality here. And then you compute, you look at the row ball around x of radius delta. So delta is at most 3 times the length of this here. So if you put yourself to be somewhere here, then you actually reach this part here, this part here, and this part here. So no ball of radius delta captures more than 3 of those segments. So that's what you use. And then you go and you evaluate the probability mass on this ball, and you upper bound it by 3 times the probability mass on any of those segments. And this is equal to the length of the segment raised, of course, to its dimension. And then you use the fact that your delta is larger than 3 to the minus g delta, and then you get subregularity of the correct dimension, the dimension of your middle third Cantor set. Okay, so it's in all cases you have seen subregularity is relatively easy to verify. And once you have that, you go into this expression we have for the lower bound, and again here you get the correct dimension. The dimension, the rate distortion dimension of x is greater or equal than m. Okay, good. So now these are all lower bounds, and we had 3 examples: hyperspheres, Grassmannians, and fractals. Of course, the theory is more general than that, and you have seen the main technical arguments are Fubini's theorem and subregularity. That's all there is technically. There's a lot of mess around it with lots of conditions on h mu has to be finite and so on. So please ignore all that. The basic idea is just a layer cake argument combined with subregularity. And then you actually get all those known results as special cases, and you get the correct lower bounds on the rate distortion dimension. So now in the second part of the talk, we want to match those lower bounds by upper bounds. And in order to establish that indeed we can compress to the limit that is induced by the dimensionality of the object that we are interested in. And the way we do this is, now if you think back, I told you one of the most striking features of rate distortion theory, or the most striking feature, is that joint encoding is better than individual encoding. We are going to look at individual encoding. Why? Because it's mathematically much, much simpler than joint encoding. And we are not going to be interested in the rate distortion function, just the dimension, okay? So it turns out that if you look at individual encoding, mathematically, you can go much further and you will get actually the correct dimension here. You won't get all the rest to match, and you will get relatively loose upper bounds, but the dimension you will get correctly. And the reason being is that individual encoding is much easier to analyze than joint encoding, okay? And that's the end of the story, essentially. So now I'm going to show you how you can finalize all this. So same setup as before. Now just think of not a sequence of ID random variables, but just mapping random variable from x to y, and the cardinality of the set that you're mapping to is upper bounded by n, and you're looking at the infimum over the expectation of whatever the error over all f's that are actually in the set of so-called n quantizers that take x to y, and the cardinality condition would be satisfied. Okay, now equivalent definitions. So we define quantization dimension, and this is something I would like to very briefly explain how this quantization dimension relates to the rate distortion dimension. So the rate distortion dimension was of order k was this. Now this by the lower rate distortion dimension. So now you can replace d by d to the 1 over k. You get and then you get k times rx of d divided by log 1 over d. So d is the distortion. Now if you compare, if you compare this to what we have here, if you map to a set of at most n values, what is the number of bits you need to represent those n values? Log n, okay? So this log n here corresponds to this rate here. So we have the k that multiplies, and we have log 1 over the distortion. Okay, so this is commensurate with our rate distortion dimension. And then you also can, of course, be interested in the coefficients. I'm not going to talk much about the coefficients, we just put things down for completeness. By the way, I would like to alert you to a book by Graf and Bölcskei in 2000 that is, I think, not nearly as much known as it should be. So this book is actually what got us started in all this. Okay, I really like the book. I mean, so if you get a chance, it's worthwhile to look at it. We has many results that we built on. And it's also a book where you can go in and you don't have to read all the way to the point where you want to extract the result. It's really self-contained to the level of subsections and so on. And for some reason, I don't know, I mean, information theorists that work in rate distortion theory usually would know the book, but anyways, it deserves to be much more known than it is. So that's good reading for, you know, I heard that Charlie always reads math books for breakfast. So maybe that's your next breakfast math book to read. So what are the known results on quantization dimension? And this is actually what we're going to be using in the second part of the talk. The quantization dimension, dk of x that we just defined, is greater equal than max of the Hausdorff dimension, again, of our measure, or the lower rate distortion dimension. So this is a very general result here. And then there is, of course, stronger results if mu x is norm regular in some norm of dimension m, then you get equality here, and then there's results of the coefficients. I don't want to go there. I mean, for coefficients, I think these are details. We're interested in the degrees of freedom. So we are going to use the fact that the lower rate distortion dimension, which we lower bounded, is upper bounded by the quantization dimension. And the question is now, can we compute the quantization dimension for these objects of interest that we looked at? Hyperspheres, submanifolds, fractals, and so on. And the answer is yes, we can do that. The upper bound is loose, as I said, but it gives us the correct number of degrees of freedom, and that will be the end of the story. Okay, so here's the lower bound that we get. Looks like this. Okay, where does this sigma p come from? Well, we always have this condition that we look at measures that are absolutely continuous with respect to a reference measure mu, and the reference measure mu is subregular. It turns out that subregularity is inherited by mu x with a different subregularity constant, and it's actually proportional to this here, and this comes by applying Hölder's inequality. So fairly straightforward. Good, so that's our lower bound. What is interesting is, again, just look at the term that contains n, because we know that log n is our rate. If we take the log here, then we get, and this p here, you can think of it as equal to 1. I mean, we just wanted things to be more general in case this is not finite for p is equal to 1. So p is 1, and then you get k divided by m, and then you look at this for order k, and then you can see how actually, given the definition that we had here, you have n to the power of k divided by the dimension, okay? and likewise here, n to the power of k divided by the dimension. This is your m. That's what we are after. Okay, the rest is all details. Okay, so this lower bound again generalizes results that were reported in Graf and Bölcskei for all sorts of special cases to arbitrary x, y, rho, and mu. In particular, the most important result that we're going to use is this here. So for arbitrary spaces x, y, you can actually get that the quantization dimension is greater or equal than the lower rate distortion dimension. This is what we're going to be interested in. And again, the rest I would ask you to ignore on this slide here. So we're going to work with this here. And now we're going to ask ourselves, first of all, how is subregularity put to use in the derivation of this lower bound? And secondly, how can we close and match the upper bounds with the lower bounds? So just a few things. The idea is just like in rate distortion theory, it works here again. Let me start with the next slide. We are going to express the distortion again by applying Fubini's theorem. And then you get to evaluate this measure here. And this measure, we actually use a lower bound and then a union bound here. Essentially, those are the quantization centers, and this is rho balls around the quantization centers. And then you get the measure of x on this rho ball. And since subregularity is inherited by mu x, if mu x is absolutely continuous with respect to mu, you can insert here the subregularity condition. And then this is what you get here, is greater or equal than 1. This is, of course, the measure of x, the total measure, minus n. N is the cardinality of the number of quantization points, c times delta to the m. So that comes from subregularity. And this uses the cardinality of your quantization scheme. And then you insert that here, and we work it out here for a special case. And that's what you get for your lower bound. So again, very simple. There's a union bound, use Fubini's theorem, subregularity. It's the same as in rate distortion theory. Just happens so that because we no longer have this aspect of joint encoding, things become much easier, and we can actually indeed extract the correct number of degrees of freedom. So let me finalize here. To recall, if we have hyperspheres, we found that the rate distortion dimension is lower bounded by d minus 1. Under a mild regularity condition, so this generalized entropy has to be finite. We actually can prove in quantization theory that our quantization dimension, the lower equals the upper, and it's equal to d minus 1. This is quite easy to work out for hyperspheres. And once you have that, you use this inequality here, which we proved holds for arbitrary spaces x and y. And then we know that dim Rx is greater or equal than d minus 1. We know that this is equal to d minus 1, and we have established the lower rate distortion dimension for hyperspheres. And it will be the same for submanifolds and for fractals. So if you have, sorry, for Grassmannians. Grassmannians set up from before, regularity condition. You can work out the quantization dimension explicitly. It's you can look it up in the paper. It's not much in terms of calculations. I mean, it's about a page or something. And then you again use the sandwich argument. You know that dim R is greater or equal than mg, and you know this here. You combine it, sandwich it, and you get the correct rate distortion dimension. And finally, for fractals, also here, relatively easy. The idea in working out the quantization dimension for fractals is I showed you how to verify subregularity. It's similar. You have to organize all the paths through your fractal and then just count them properly. And then that's how you get the correct dimension here. And again, sandwich argument, and you are done. And all that you can do for very general structures. Okay, so these are just 3 examples. And in the paper, you have the general theory, and there's other structures you can have. And that concludes my talk. If there are any questions, and thank you very much for listening.